small and closer to the Sun than any other planet, Mercury is where the extreme limits of nature are tested in ways that are almost unimaginable. With temperatures soaring up to 430 degrees Celsius during the day, hot enough to melt metal, yet plummeting to minus 173 degrees Celsius at night, cold enough to freeze steel. Along with this, Mercury holds the marks of the early solar system, recording fierce laws of nature. Composed of 70% metal, with its metal core making up about 85% of its radius. Mercury stands as one of the heaviest planets. The truth about Mercury is even more mysterious when we discover that this planet has a sodium tail stretching up to 2.5 million kilometers, an invisible streak only visible through modern technology. This is just the beginning. Now, we'll step into the world of Mercury, considered the most extreme planet in the solar system. We've seen the extreme temperature contrasts on Mercury. But in reality, this opposition goes even further, challenging the very logic of physics. This is Mercury's first and perhaps greatest mystery. With its unprecedented temperature swing, imagine this, in just one day, the planet's temperature jumps from 430 degrees Celsius, enough to melt molten metal, down to minus 173 degrees Celsius, colder than any night on Earth. This nearly 600 degree Celsius difference is a direct result of the planet's almost non-existent atmosphere. With no atmosphere to retain heat, all the solar energy absorbed is radiated back into space immediately once night falls. Mercury has almost no atmosphere. This thin air is not enough to trap the heat from the sun. So how can Mercury still have ice in a world with such extreme temperatures? It was the radar from the Arecibo Observatory that discovered something peculiar. Eternal water ice exists at Mercury's poles. Deep craters near the planet's poles create areas of perpetual darkness, untouched by sunlight, where temperatures remain frozen despite the scorching heat around the planet. These areas act like natural ice containers, where water could be preserved for billions of years without melting. Scientists hypothesize that ancient comets or celestial collisions in the past may have brought water deep into these craters. How can Mercury, a planet with almost no atmosphere, manage to keep water in these dark regions? We are faced with a mystery that goes beyond just the existence of ice on this planet. This opens up questions about the origins of life in the solar system, if Mercury can preserve water ice in these shadowed regions. Could we one day find traces of life in ice? Just as we found water traces on distant planets, the existence of water ice challenges logic, but to study it, scientists must overcome a greater physical challenge: the relentless gravitational pull of the sun. The journey to Mercury is a battle against gravity. As the increasing speed of the spacecraft when it enters the sun's orbit is one of the greatest difficulties. The sun's immense gravity continually pulls the spacecraft, accelerating it at an astonishing rate. This pull is so strong that without proper deceleration, the spacecraft would simply zip past Mercury and be drawn into the sun. This creates a problem no one could foresee when embarking on an exploration to this planet. BP Colombo, the spacecraft currently en route to Mercury, must cover a distance of 8.5 billion kilometers. And this is not just a simple trip to a planet. It's a challenging journey that requires the spacecraft to make 18 orbits around the sun, with 9 flybys of other planets like Earth, Venus, and Mercury. But why can't it fly directly to Mercury and instead has to take such a winding path? The answer lies in the sun's own gravitational pull. To slow down, BP Colombo had to employ a highly creative strategy, taking a detour to harness the gravitational forces of planets to reduce the craft's speed. Throughout this journey, ion engine technology plays a crucial role. This engine uses continuous blue light to generate gentle thrust, allowing the spacecraft to avoid being sucked into the sun while continuing its path to the planet closest to the sun. But this technology is not the only factor contributing to the success of BP Colombo's mission. As the spacecraft approaches Mercury to combat the extremely intense radiation from the sun, 10 times the radiation Earth experiences, BP Colombo is equipped with an advanced thermal shielding system made of ceramic. This system can withstand extremely high temperatures without damage, protecting the spacecraft's critical components. Especially scientific instruments and communication systems. The ceramic thermal shield is crucial in safeguarding the spacecraft from these effects. while also maintaining the stability of scientific instruments without overheating. However, the challenges don't stop there. Bepi Colombo not only has to avoid the intense heat from the sun, but must also contend with the extreme temperature fluctuations throughout its journey. Mercury's elliptical orbit presents a significant challenge in maintaining a stable temperature for the spacecraft. Bepi Colombo must rely on orbital strategies to help maintain its operational capability without overheating. Is there a way to maintain a stable temperature without relying on such a complex system? Bepi Colombo, with its modern technology and sophisticated orbital strategies, might be a temporary solution. But it's only the first step in studying and conquering the harsh physical limits of space. With current technology, the exploration of Mercury remains one of humanity's greatest challenges. Mercury is not just a planet close to the Sun. It's a natural laboratory where the laws of physics seem to be turned upside down. Deep beneath the surface of Mercury lies a physical structure that doesn't fit the pattern of any rocky planet. Imagine a tiny planet with a metal core that makes up 85% of its radius, making Mercury the second densest planet in the solar system, only behind Earth. Why does Mercury have such a massive metal core? Recent studies, particularly from the Bepi Colombo mission, have given us new insights into Mercury's internal structure. Data from the Bepi Colombo spacecraft is revealing that Mercury's metal core isn't just a solid mass. It's still hot, indicating that the planet has not fully cooled since its formation. One popular hypothesis for Mercury's origins is the giant impact theory, which suggests that in the early days of the solar system, the planet underwent an extremely powerful collision. This collision blew away Mercury's rocky mantle, leaving behind a dense and heavy metal core. Current research shows a surprising fact. When the Sun was young, its radiation power might have blown light materials off the planet's surface, leaving only the metal core beneath. This is a new discovery that helps us better understand the planetary formation process in our solar system. Another mystery scientists are trying to solve is the fact that Mercury is slowly shrinking. Large cracks on the surface. Like the Beagle-Roup's Ridge, are evidence that the planet has shrunk by over 14 kilometers during its history. This suggests that Mercury's metal core continues to cool and contract over time. Scientists believe that as Mercury's metal core cools, the planet began to shrink and crack. These cracks, or lobate scarps, are clear signs that the planet has experienced significant geological activity in the past. But beyond the planet's shrinkage, another issue causing debate in the scientific community is the existence of energy within Mercury. The question of Mercury's metal core remains a challenge. How has Mercury managed to maintain a hot metal core throughout its history? And can we truly understand the structure and evolution of this planet by studying the fluctuations within Mercury's core? We once assumed that Mercury was a barren, sun-scorched world, riddled with impact craters and completely silent, much like a distorted version of the Moon. But is this silence perhaps the greatest misconception in planetary science? Groundbreaking data from two major missions, the NASA's Messenger spacecraft and the recent Bepi-Colombo mission, a collaboration between Europe and Japan, have uncovered a startling secret. Mercury, in the dawn of the solar system, was not only boiling but has kept an internal fire far longer than we thought, making it a living witness to planetary geological transformation. Let's start with the Caloris Basin, a colossal impact crater with a diameter of 1,550 kilometers, a geological scar roughly the size of Texas. For a long time, it has been considered the clearest evidence of the solar system's late heavy bombardment. But is it just a simple impact crater? Detailed images have revealed that Caloris is not merely a basin. It is a vast fossilized lava sea. More importantly, at the center of Caloris lies an unusually deep network of fractures known as Pantheon fossae. Which has defied traditional explanations. These fractures radiate from a crater near the center, Apollodorus. Scientists believe that the explosive force of the impact created a shock wave that traveled across the entire planet, fracturing its fragile crust and allowing magma from deep beneath the surface to surge up, filling the basin and creating the smooth plains we see today. Before the data from Messenger, scientists believed that volcanic activity on Mercury ceased billions of years ago. However, researchers have identified regions with flat, smooth plains covered by a slick material. showing few small craters, clear signs of relatively young lava flows that erased older geological structures. Notably, the discovery of supervolcanic eruptions unrelated to impacts, such as Navoy Mons, has been a game changer. These eruptions occurred when volatile materials, things that seemed impossible to exist on a planet so close to the Sun, were heated by magma and expelled into space, forming pits or cracks on the surface. However, recent research has uncovered salt-like glacier structures in craters near the North Pole. Including prominent double-ring craters like Rachmaninoff and Raditladi. Planetary scientists believe these structures are not just salt, but may also contain other volatile compounds, trapped and preserved for billions of years beneath the surface. This is a revelation that completely changes our perspective. While Mercury's surface is as harsh as a furnace, these subsurface areas may be far more hospitable. Could these salt glaciers, which preserve essential compounds for life, create a stable environment capable of nurturing some mysterious form of microorganism deep underground, shielded from the sun's scorching heat? Compared to the Moon, a planet whose surface Mercury seems to mirror. Mercury has revealed a much more complex and dynamic geological history. Evidence of that ancient fire is still perfectly preserved in the form of fossilized lava seas, tectonic fractures, and traces of supervolcanic eruptions. Mercury was once a furnace, but what has allowed it to maintain enough energy in its massive metal core to create one of the greatest paradoxes? Could it be the magnetic field? Previously thought to be impossible due to its small size and high temperatures. Missions like Mariner 10 and Messenger have reshaped how we perceive this planet. Mercury does indeed have a magnetic field, although it is weak, only about 1.1% of Earth's. This came as a surprise to scientists, as theory suggested that such a small planet would not have enough energy to sustain a magnetic field. Mercury's magnetic field is asymmetric, with its magnetic center offset by 20% from the planet's physical center. Is one of the greatest anomalies among all planets with magnetic fields in the solar system. Why this offset? What creates a magnetic field that is so asymmetrical, unlike any other planet in the universe? Mercury's magnetic field mechanism involves the dynamo process, the flow of molten metal in the planet's core. However, unlike Earth, where a sufficiently large solid and liquid metal core generates a strong magnetic field, Mercury has a large molten metal core but lacks a strong energy source. Scientists believe that the Sun's tidal forces may be the key to generating the energy necessary to maintain Mercury's magnetic field. The tidal forces, created by Mercury's elliptical orbit, generate continuous physical waves that stir the planet's metal core, keeping the molten metal flowing and creating a weak but persistent magnetic field. One of the strangest aspects of Mercury's magnetic field is its misalignment. The planet's magnetic field is not only weak, but also so offset that it challenges existing geophysical models. This anomaly not only challenges current theories, but also opens up entirely new avenues of research into planetary geophysical mechanisms. Could Mercury's misaligned magnetic field be a manifestation of magnetic field formation processes in planets close to the Sun? Or is it just a unique case? Although this planet has no atmosphere and conditions for life seem impossible, Mercury's weak magnetic field might still create some of the necessary conditions for geological processes. Perhaps this field, despite its weakness, plays a crucial role in maintaining stability and protecting the planet from the intrusion of factors from deep space. Mercury's magnetic field may not be as strong as Earth's, but its existence could be the key to a deeper understanding of the development and structure of this planet. With the advent of Bepi Colombo and future missions, we may soon make unexpected discoveries about Mercury's magnetic field. Its weak, yet asymmetric magnetic field, along with the findings from current missions, will continue to help us gain deeper insights into this mysterious planet. Beyond its weak magnetic field, this planet interacts with the Sun in a unique way that's unlike anywhere else in the solar system. Without an atmosphere, yet it has a tail. Mercury lacks an atmosphere like Earth's, but in reality, it has a very thin exosphere. This is the layer of gas that is constantly bombarded by the solar wind. A stream of charged particles, blowing atoms from Mercury's surface into space. In this exosphere, elements such as helium, potassium, sodium, and hydrogen float around, creating a strange interaction between the planet and the Sun. But what's even more remarkable is this strange visual phenomenon that forms a glowing streak stretching millions of kilometers behind Mercury, turning it into a metallic comet for eternity. This glowing trail, called the metal tail, can extend up to 2.5 million kilometers. This is not a simple solar wind phenomenon, but rather the result of the solar radiation pressure force. Sunlight, through photon force, pushes sodium atoms off the planet's surface, creating the characteristic metal tail. This phenomenon is an extremely unique physical mechanism. While we know the solar wind can blow material off planets, it's the interaction with sunlight that is the main factor creating an endless tail extending from Mercury. What makes this magic happen? The answer lies in the photons from the sun, which continuously push sodium atoms into space. Mercury, a planet with no atmosphere like Earth, but with a metallic tail extending millions of kilometers, the interaction between Mercury and the Sun is not limited to material loss, but also reveals profound effects from radiation and the planet's orbit. Mercury's exosphere is not just a thin layer of gas. It's the key to unlocking answers about the interactions between the planet and the Sun. The surface of Mercury holds mysteries that can only be found here, serving as the clearest evidence that it defies all assumptions of a quiet, static world. This planet, barren and scorching, still maintains powerful movements at the molecular level. The Pantheon-Fosse structure, with its starburst-like network of fractures, continues to challenge theories of geological development. It is a testament to the internal stress from the massive metal core that still impacts the crust, showing an ongoing, albeit slow, transformation despite the harsh environmental conditions. This journey of exploration does not stop at curiosity. The Bepi Colombo mission will complete a map of Mercury's magnetic field and exosphere by around 2030. Promising a breakthrough in unraveling the big questions about its origin and evolution. Mercury is slowly changing, holding the answers to the formation of the entire solar system. The geological and chemical traces it leaves behind are not just phenomena, but keys to a deeper understanding of life and the evolution of the universe. throughout the history of our planet, life has faced 5 major mass extinctions, each leaving deep and lasting marks on the surface of Earth. From the Permian extinction, when roughly 90% of marine species and 70% of land-dwelling organisms vanished around 252 million years ago, to the most recent extinction about 66 million years ago, when an asteroid struck Earth and led to the downfall of the dinosaurs. How was life able to recover and endure through catastrophes of such scale? Research suggests that life is not merely a chain of random events. It is a complex process shaped by ecological and geological forces. The species that survived were often those with exceptional adaptability, capable of enduring extreme environments. Moreover, traces of life persisting after these disasters are frequently found in the fossil record, revealing that life consistently finds a way to regenerate, even when confronted with the harshest conditions imaginable. Right now, let us move closer to these challenges. Around 445 to 444 million years ago, Earth faced a trial that did not come from a lack of nutrients or oxygen, but from extreme cold. This was the first time life nearly froze completely in a world where glaciers spread and the oceans retreated. Before the catastrophe, Ordovician Earth appeared stable and prosperous. Average global temperatures were about 2 degrees Celsius higher than today, and sea levels stood nearly 600 meters above modern levels. Most continents were submerged beneath shallow, warm, sunlit seas. An ideal environment for biological expansion. Life was almost entirely concentrated in the oceans. Continental shelves became centers of evolution, where primitive corals, brachiopods, mollusks, trilobites, and countless other invertebrates formed complex ecological networks. When these foundational conditions began to change, the entire marine biosphere became vulnerable. And that change was driven by an irreversible geological process. The supercontinent Gondwana slowly drifted toward the South Pole. At the same time, atmospheric carbon dioxide levels declined, partly due to intensified silicate weathering and long-running natural chemical cycles. As carbon dioxide fell, the greenhouse effect weakened, and Earth began to lose heat. Massive ice sheets formed on Gondwana, reflecting sunlight back into space and creating a self-reinforcing cooling feedback loop. Over a relatively short geological interval, ocean temperatures dropped by about 4 degrees Celsius. As the ice expanded, sea levels fell rapidly by roughly 100 meters. The shallow continental shelves, home to most marine life, were exposed or vanished altogether. Entire ecosystems lost the space they needed to exist. Organisms could not retreat to deeper waters fast enough, nor could they adapt quickly to lower temperatures and shifting oxygen conditions. No asteroid was required. No volcano was needed. Habitats simply disappeared beneath life itself. The result was the extinction of roughly 85% of marine species, one of the highest loss rates ever recorded. What makes the Ordovician extinction distinct is how it killed, not through direct destruction, but by draining away the minimum conditions required for survival. As sea levels dropped, ocean currents shifted, and the distribution of oxygen and nutrients was thrown into chaos. Food chains collapsed from the bottom up. Species adapted to warm, shallow, well-lit waters were left with nowhere to cling. Extinction unfolded in silence, cold, relentless, and unforgiving. Stratigraphic data reveal that this catastrophe occurred in at least 2 extinction phases. The first struck when glaciation reached its peak and sea levels plunged. The second followed as the ice melted and the climate warmed again relatively quickly, triggering widespread oxygen-depleted zones in the oceans. Life, then, was not tested by cold alone, but by the speed of climatic reversal. It was not heat or cold by itself that proved lethal, but environmental change occurring faster than biological adaptation could keep up. The organisms that crossed the Ordovician boundary were primarily seafloor dwellers, living in deeper waters where temperatures were more stable and less affected by sea level fluctuations. Early bony fish, though still simple in form, possessed a broader tolerance for environmental stress than many highly specialized invertebrates. They did not dominate, they were not diverse. But they did not disappear, and in evolution, survival alone is often enough. Despite the immense death toll, this catastrophe did not destroy the foundations of vertebrate life. Instead, it filtered the biosphere in a brutal way, removing forms of life that were too dependent on stable conditions. From those few survivors, major evolutionary lineages continued to develop in later periods, laying the groundwork for the entire history of vertebrates on Earth. From this near-total freezing, a fundamental rule begins to emerge. Life persists not because it avoids catastrophe, but because it can endure and recover from it. The survivors were not lucky exceptions, but expressions of very specific biological traits. Low resource demands, high tolerance, and deep integration with the planet's fundamental cycles. between roughly 372 and 359 million years ago. Earth entered a period in which progress on land became the very cause of collapse in the oceans. The late Devonian mass extinction emerged from a long chain of biological and geochemical transformations, marking the first time life itself generated a planet-scale crisis. During the Devonian, the oceans were the center of biological complexity, with armored fish giants, early sharks, diverse mollusks, and vast ancient coral reefs stretching across continental scales. Marine food webs reached a rare state of stability, crowned by apex predators such as Dunkleosteus, a heavily armored creature more than 6 meters long, with a bite force powerful enough to crush bone. The Devonian seas appeared complete, a world seemingly with no room left for disruptive change. Yet while the oceans thrived, the continents were undergoing a profound transformation. The first true forests emerged and spread. Plants were no longer low mats clinging to the ground. They developed woody trunks, deep root systems, and rose upward to capture sunlight. This was a biological revolution because for the first time, life on land began to interact intensely with geology. Carried by river systems, these nutrients poured into the oceans at rates far beyond natural balance. The surplus fueled widespread blooms of algae and bacteria. At first, the oceans seemed more productive than ever. But as these organisms died, their decomposition consumed vast amounts of dissolved oxygen. Gradually, large portions of the ocean slipped into low oxygen conditions, and in many regions, oxygen disappeared entirely. Geochemical evidence, organic-rich sediments, sulfur and iron isotope signatures reveals that oxygen depletion spread not only through deep waters, but also across shallow continental seas. Roughly 75% of marine species vanished during this prolonged extinction sequence. Devonian coral reefs collapsed almost completely and would not reappear in new forms for tens of millions of years. Large, highly active animals with high oxygen demands, including Dunkleosteus itself, could not survive in a suffocating ocean. The dominance of armored fishes ended not because of biological competition, but because of chemical changes in their environment. What sets the Devonian extinction apart from other catastrophes is its duration and fragmentation. This was not a single sharp extinction boundary, but a series of repeated declines, each weakening ecosystems a little more. life did not vanish in an instant. It was gradually eroded, while the underlying causes arose from changes that seemed progressive elsewhere. At a deeper level, this marked the first time in Earth's history that life acted as a geological force. Land plants drew down carbon dioxide, stabilized climate, and created fertile soils. Outcomes traditionally viewed as beneficial. Yet that very success destabilized the oceans for the first time. Life generated a global negative feedback against itself. There was no intention, no awareness, only the inevitable consequences of evolution. Small, bottom-dwelling organisms with low oxygen requirements, or those capable of enduring harsh conditions, survived within biological refuge zones. More importantly, however, one group of organisms began to face an unprecedented evolutionary choice. As the oceans, the cradle of life, became increasingly hostile, staying was no longer the safer option. In shallow waters, swamps, and river deltas, lobe-finned fishes such as tiktaalik emerged. These were not creatures that suddenly walked out of the water, but organisms that lived between two worlds. The Devonian extinction did more than eliminate the most powerful marine life of its time. It redirected the course of vertebrate evolution. "252 million years ago, Earth came frighteningly close to the final boundary for complex life. Through a prolonged, relentless, and brutally unforgiving process, the planet nearly suffocated itself. The Permian-Triassic extinction was not merely a decline in biodiversity. It was the greatest biological catastrophe ever recorded. A moment when life support systems collapsed layer by layer across the entire planet. Geological and fossil evidence shows that roughly 96% of marine species vanished, along with about 70% of life on land. These conclusions are the result of decades of analysis of rock strata, species diversity, and biological markers before and after the Permian-Triassic boundary. Ancient coral reefs were almost completely erased. Entire groups of organisms that had survived for tens of millions of years abruptly reached the end of their evolutionary history. The cause did not come from beyond Earth. It rose from deep within the planet's mantle. It rose from deep within the planet's mantle, in what is now Siberia. A massive series of basalt eruptions, known as the Siberian traps, began to unfold. This was not a single volcano, but a continent-scale eruptive system that persisted for tens of thousands of years, possibly longer. Lava flooded millions of square kilometers, and more critically, released enormous quantities of carbon dioxide, methane, and sulfur dioxide into the atmosphere. As carbon dioxide levels surged, Earth was pushed into an extreme greenhouse state, driving average global temperatures up by roughly 5 to 10 degrees Celsius. This increase was enough to shatter biological balance on a planetary scale. The oceans warmed, and as water temperatures rose, their ability to hold oxygen dropped sharply. Widespread oxygen depletion followed, especially in mid-depth and deep waters. Dead zones were no longer isolated phenomena. They became the dominant condition. At the same time, carbon dioxide dissolved into seawater, forming carbonic acid and triggering ocean acidification. Once the foundation of marine food webs collapsed, higher levels could not survive. Global food chains fell apart from the base upward, with no capacity for recovery. What makes the Permian extinction truly terrifying is not only the scale of death, but its systemic nature. There were no safe havens, no ecosystem was immune. As the oceans suffocated, land environments followed. Plant life declined, soils eroded, and nutrient cycles broke down. Nutrients washed into the seas, further fueling bacterial blooms that consumed what little oxygen remained. It became a positive feedback loop where each failure intensified the next. In this environment, large, specialized organisms with slow reproductive rates had almost no chance of survival. Microorganisms capable of flexible metabolism and extreme tolerance endured and continued to sustain carbon and sulfur cycles. Some tiny animal groups, such as ostracods, with modest size and rapid life cycles, managed to pass through a period in which nearly everything else failed. At a deeper level, the Permian extinction stands as a stark warning that Earth is not always a gentle world. When physical and chemical thresholds are crossed, the planet itself can become hostile to the life that evolved upon it. Earth persists through a fragile balance between geology, climate, and biology. A balance that can be broken from within without any cosmic trigger. And yet, from the ashes of the greatest catastrophe in Earth's history, a new era slowly emerged. with former dominance gone and ecosystems rebuilt from the ground up. Organisms best suited to a post-disaster world began to rise. Evolutionary pathways reopened, not for those who once ruled, but for those capable of adapting the fastest. Around 201.3 million years ago, Earth entered a quiet yet decisive turning point. A moment when the history of life was not written through total annihilation, but through a shift in evolutionary power. The extinction at the end of the Triassic and the beginning of the Jurassic opened the way for the age of dinosaurs. At the close of the Triassic, Earth was still locked into the form of the supercontinent Pangaea. This vast landmass stretched from pole to pole, producing an extreme global climate. Arid continental interiors, unstable coastlines, wide temperature swings, and ecosystems perpetually under stress. As Pangaea began to break apart, the planet's crust split along its weakest zones, triggering a series of continent-scale basalt eruptions known as the Central Atlantic Magmatic Province, or CAMP. This was one of the largest volcanic events in geological history, covering millions of square kilometers and unfolding through multiple eruptive pulses over hundreds of thousands of years. It was not a single explosion, but a sustained barrage against the global climate system. Each eruptive pulse released massive amounts of carbon dioxide and other greenhouse gases into the atmosphere, pushing Earth into rapid and unstable warming. Geochemical evidence shows significant rises in global temperature, disrupted climate cycles, and alternating periods of severe drought and intense rainfall, shattering already fragile ecological balances. The oceans were hit from two directions. Warming waters reduced oxygen solubility, while dissolved carbon dioxide drove ocean acidification, damaging organisms with carbonate skeletons. The result was the loss of roughly 70 to 80% of all species, enough to erase much of the planet's existing biological structure. The Triassic world had been dominated by other ancient reptile groups, large predators within the pseudosuchians and a wide range of reptilian forms occupying diverse ecological roles. Dinosaurs at this time were only a minor branch, limited in distribution, relatively small in size, and confined to narrow ecological niches. When environmental change accelerated beyond a critical threshold, evolutionary advantages were reversed. Large, highly specialized species dependent on stable food webs and slow reproductive rates became increasingly vulnerable. Dinosaurs, by contrast, possessed a combination of biological traits that were largely accidental, yet decisive. Their upright posture, supported by powerful hind limbs, allowed for more efficient movement and reduced energy costs in harsh environments. Highly efficient respiratory systems, with one-way airflow through the lungs, enabled better oxygen exchange under hot and oxygen-poor conditions. Egg-laying reproduction and relatively fast growth rates allowed their populations to rebound quickly after environmental shocks. These traits made dinosaurs less likely to be eliminated than many competing groups. As dominant rivals collapsed, ecological space opened everywhere, from top predators to large herbivores. Over the following millions of years, as Pangaea continued to fragment, new continents formed, climates diversified by latitude, and oceans widened, the world became richer in available habitats. Within this changing landscape, dinosaurs underwent an explosive diversification in form and size. From colossal long-necked herbivores reaching into forest canopies to agile predators and small, elusive species, dinosaurs came to occupy nearly every terrestrial ecological role. Their dominance lasted for roughly 135 million years, longer than the entire history of humanity to this day. After dinosaurs had ruled the planet for roughly 175 million years, a rare but decisive cosmic event took place. 66 million years ago, at the end of the Cretaceous period, an asteroid approximately 10 to 12 kilometers in diameter slammed into Earth at a speed exceeding 20 kilometers per second. Striking what is now the Yucatan Peninsula in Mexico. The energy released in that instant surpassed anything humanity has ever experienced. In the first few minutes, Earth's crust shook violently. Seismic waves raced around the planet with an intensity greater than any earthquake recorded in modern history. Along the oceans, transcontinental tsunamis, hundreds of meters high, swept across coastlines, erasing coastal ecosystems within hours. For months, and even years afterward, sunlight was drastically reduced. Photosynthesis, the energy foundation of nearly the entire biosphere, collapsed on a global scale. Plants died en masse, triggering a cascading breakdown of higher trophic levels. paleontological research indicates that roughly 75% of Earth's species disappeared during the Cretaceous-Paleogene extinction. Non-avian dinosaurs, the long-standing rulers of the land, could not survive this ecological shock. Not because they were weak, but because they were too large, too specialized, and too dependent on stable ecosystems. Some species may have survived the initial day of impact, even enduring the global wildfires ignited by showers of incandescent debris raining back down to the surface. But when the skies remained dark for extended periods and plant life failed to recover, massive bodies with high energy demands became a fatal liability. Small organisms with fast reproductive cycles, flexible diets, and the ability to shelter, such as burrowing animals, semi-aquatic species, or those capable of subsisting on organic debris, had a better chance of enduring the prolonged darkness. Microorganisms, especially bacteria and single-celled algae, continued to sustain basic biogeochemical cycles, preventing the planet from slipping into complete biological collapse. It is here that the Chicxulub event forces us to rethink what strength truly means in evolution. 175 million years of dominance did not guarantee survival when the planet's foundational conditions were overturned in a geological instant. Nature does not favor the biggest, the fastest, or the most fearsome. It preserves only what can adapt quickly enough to a transformed world. The Cretaceous-Paleogene extinction was, in truth, only a brief pause within the universe's long and turbulent history. Life did not shape Earth by design, it merely adapted to it by chance. The 5 previous mass extinctions did not erase life entirely. Instead, they served as turning points, moments that reshaped the biosphere and propelled evolution forward. What we face now, however, is fundamentally different. The 6th mass extinction did not begin with cosmic impacts or geological upheaval. It began with us. With extinction rates now running 100 to 1,000 times higher than natural background levels, humanity has become the only species in Earth's 4.5 billion-year history to trigger a global biological crisis by its own actions. As ecological links snap at unprecedented speed, We are not only stripping the planet of biodiversity, we are undermining the very foundations of our own survival. And yet, when viewed across millions of years, life itself is far more resilient than human imagination allows. Even if humanity fails to adapt to the changes it has set in motion, Earth will continue on its path. New ecosystems will form. New forms of life will rise from the ruins of the present age. The central question we now face is not whether life will endure, but whether, in the next chapter of the universe's history, humanity will still be part of that story, or merely a thin fossil layer embedded in stone. Since Galileo Galilei first turned a telescope toward the heavens in 1609, humanity has embarked on a timeless journey to search for signs of life beyond Earth. Yet in recent years, research has brought astonishing discoveries, opening an entirely new vision of what might be possible. One of the most remarkable findings came from NASA's Cassini mission. Plumes of icy water erupting from Saturn's moon Enceladus, rich with complex organic molecules, the essential building blocks of life. But that's not all. New theories about subsurface oceans on Europa, Jupiter's enigmatic moon, supported by data from the Hubble Space Telescope, promise to reveal more about the hidden environments that may nurture life beneath the ice. At the same time, scientists have identified habitable zones on planets beyond our solar system. Worlds like Kepler 452b, whose atmosphere and temperatures mirror those of Earth. We have uncovered fascinating clues, but the question remains, does life truly exist out there? The evidence is growing clearer, and the answer, perhaps, is closer than we ever imagined. To truly understand where life might exist, we must look beyond Earth-like environments and explore conditions utterly different from our own, where the laws of science themselves might behave in unimaginable ways. The first thing scientists look for when observing a distant planet is the habitable zone, often called the Goldilocks zone. This is the region around a star where temperatures are just right for liquid water to exist. A key ingredient for life as we know it. This concept comes from the belief that life requires water to develop. And water can only remain in liquid form within a specific temperature range. In our solar system, planets like Venus and Mars have extreme conditions. Too hot or too cold to sustain liquid water, making them inhospitable. However, planets such as Kepler 452b, a super-Earth located about 1,400 light-years away, exist within the habitable zone of a Sun-like star. Such worlds could potentially support life, provided they have liquid water. But this raises a deeper question. Is liquid water alone enough? Recent studies suggest that life might require more than just the right temperature and water. Carbon forms the backbone of all complex organic molecules, from proteins to DNA, and it is the foundation of every living structure. Carbon chains allow the creation of cells, the basic building blocks of life. For this reason, carbon is considered the essential element for life as we know it. However, in the search for extraterrestrial life, one critical question emerges. Could life exist without carbon? Scientists have begun exploring alternative elements that might support life. One such candidate is silicon, the element directly beneath carbon on the periodic table. Silicon can form chemical bonds similar to carbon, leading many researchers to speculate that alien life might be based on silicon instead. Yet silicon's molecular structure lacks the flexibility of carbon. Its bonds are less adaptable, making it difficult to form the complex dynamic structures associated with advanced life. Still, that doesn't mean silicon-based life is impossible. Could there be life in worlds utterly unlike Earth? One fascinating discussion centers on the possibility of non-traditional life thriving in exotic atmospheres. For example, Venus, with its clouds of sulfuric acid and surface temperatures hot enough to melt lead, would seem utterly inhospitable. In addition, life may exist not only on the surface of planets but also in the temperate layers of the atmospheres of planets with extreme conditions. Scientists have suggested that life might develop on a planet with a dense atmosphere. Not from the surface, but within the higher cloud layers, where water molecules could exist without being destroyed by the planet's surface heat. To find the answer to this question, scientists have had to expand the scope of the search for life. They are not only looking for traces of water or oxygen, but also for methane, phosphine, and complex organic molecules that may appear in the atmospheres of distant planets. These gases could be products of biochemical processes we do not yet fully understand, or they could be traces of life. One of the latest discoveries relates to the presence of phosphine in the atmosphere of Venus, a gas that is very difficult to form under natural conditions without the involvement of biological processes. This has made scientists reconsider the possibility that life could exist in an environment as extreme as Venus. Could life exist in a form unlike Earth's within this special atmospheric environment? The answer is gradually being revealed through clues found in research, and these discoveries could completely change the way we perceive life in the universe. If you love this topic, subscribe to WUFO now so you won't miss the next discoveries. When we turn our gaze toward distant planets in the Goldilocks zone, hundreds of millions of kilometers from Earth, there are two icy moons, Europa, the moon of Jupiter, and Enceladus, the moon of Saturn. These icy worlds may hold one of the greatest secrets in the quest to find life beyond Earth. Both of these moons share one remarkable feature. Beneath their thick layers of ice are vast oceans of liquid salt water. Environments that could be suitable for life, this is a completely new and fascinating discovery, opening many opportunities for science. Could we find life in these oceans? The answer may lie just beneath the eternal ice, where temperatures and conditions are beyond imagination. We begin with Europa, the moon of Jupiter, where data collected from the Galileo spacecraft has provided clear evidence of a global ocean beneath its thick ice. Believed to be as deep as 100 kilometers, this ocean may harbor life we have never imagined. What makes Europa special is the existence of liquid water beneath the ice. An ideal condition for life, even though it is far from the sun. The question is, how does Europa keep its water in liquid form in a cold environment without sunlight? Tidal heating, a phenomenon caused by the interaction between Europa and Jupiter. As Europa orbits Jupiter, the planet's immense gravity creates friction, heating the icy crust and maintaining subsurface temperatures warm enough to keep the water liquid. The hydrothermal vents at Europa's ocean floor could provide energy for chemosynthetic life, similar to Earth's deep-sea ecosystems, where no sunlight exists but life thrives through chemical reactions. Cooled microorganisms exist at the bottom of this ocean, living on chemical energy instead of sunlight. Meanwhile, on Enceladus, scientists have observed massive plumes of water called geysers, erupting from cracks near the Moon's south pole. The molecules in these plumes, analyzed by the Cassini spacecraft, not only confirmed the presence of liquid water, but also detected organic compounds. Particularly hydrogen, a strong indication that hydrothermal activity is occurring beneath the surface of Enceladus. The presence of hydrogen may indicate that life exists within this ocean, with methane-producing microbes thriving on hydrothermal energy. In addition, studies have shown that Enceladus's ocean is alkaline, a chemical environment highly favorable for the formation of prebiotic molecules while Europa and Enceladus offer a fascinating vision of life beneath their frozen oceans. We may have to completely rethink our understanding when confronting Titan, Saturn's largest moon. Unlike Jupiter's icy moons, Titan challenges every traditional definition of life in the universe. There is no liquid water here, but there is something else, liquid methane. Titan is not just a strange world, but one that completely breaks the model of life as we know it. Could life exist in a completely different solvent, not water, but methane? Titan is the only moon with a thick atmosphere, composed mainly of nitrogen and methane. This atmosphere is unlike any other in the solar system. The surface temperature of Titan is extremely cold, around minus 179 degrees Celsius, causing water to freeze solid. However, what's remarkable is that probes like Cassini have confirmed the existence of rivers, lakes, and seas on Titan's surface. But these lakes are not made of liquid water like those on Earth, but of methane and ethane, two liquids that exist at very low temperatures. This not only creates a strange environment, but also opens up a new concept of the liquid cycle. On Titan, liquid methane evaporates and forms methane clouds, which then rain down into lakes and rivers. This system functions much like Earth's water cycle, but with methane replacing water. Essentially, Titan is a frozen version of early Earth, a place containing all the ingredients needed to trigger prebiotic chemistry, but without water. Tholins, a type of complex organic compound, have also been found on Titan's surface. They are formed when ultraviolet light and cosmic rays react with methane and nitrogen in the atmosphere. This makes Titan a unique chemical world, resembling an early version of Earth, but without water. Instead, liquid methane serves as the main liquid in Titan's biological cycle. On Earth, water is the ideal solvent for life because it can dissolve many compounds and support key chemical reactions. But methane and ethane are nonpolar, which prevents them from dissolving compounds the way water does. However, under Titan's extremely low temperatures, liquid methane can act as a stable solvent for complex molecules, capable of supporting life. To understand this better, astrochemists have modeled molecules called azotosms, potential cell membranes that could sustain life in liquid methane. Exotosomes are made of nitrogen instead of lipids, like cells on Earth. This introduces a completely new possibility in astrobiology: that life on Titan could develop not from water, but from methane and ethane. Could these molecules self-assemble into complex structures capable of sustaining life in a cold, oxygen-poor environment? If life exists on Titan, it would not breathe oxygen or need water as we imagine. Instead, life on Titan could use the hydrogen in its atmosphere and organic molecules to produce energy in a cycle completely different from that of organisms on Earth. Titan challenges every definition we have of life. It forces us to abandon the boundaries we once believed, that life must depend on water, oxygen, and moderate temperatures like Earth's. The exploration of Titan is not simply a search for life. It is a journey to discover the limits of life in the universe. How can we confirm or reject the existence of extraterrestrial life on distant planets, tens or even hundreds of light years away? The answer does not lie in theories or assumptions, but in unprecedented advanced technologies that open a window for us to peer through the universe and search for signs of life from afar. The ability to search for extraterrestrial life has now achieved a breakthrough with the James Webb Space Telescope, JWST. JWST operates by observing light when planets pass through the atmospheres of stars in distant star systems. When the light from a star passes through a planet's atmosphere, molecules within it absorb specific wavelengths of light. The analysis of these absorbed wavelengths allows scientists to determine the exact chemical composition of the planet's atmosphere. This opens the possibility of detecting chemical fingerprints that help us identify biosignatures, biological traces that may indicate life. The extreme sensitivity and analytical capability of JWST in the infrared range will help scientists search for traces of life. Even in the atmospheres of planets located far across the universe that we have never been able to reach. When we cannot approach distant planets, studying life in outer space environments becomes the key. The International Space Station, ISS, is a permanent space biology laboratory where experiments in microgravity and intense radiation have helped us better understand the biological limits of life in the harsh environment of space. One of the most important experiments conducted on the ISS is the EXPOSE program by the European Space Agency, ESA. This experiment placed extremophile microorganisms in a microgravity environment and exposed them directly to cosmic radiation and the vacuum of space. The results were surprising. Many species of bacteria, such as Bacillus subtilis and Deinococcus radiodurans, were able to survive and even grow after being directly exposed to space for long periods. These experiments reinforce the theory of panspermia, the possibility that life can spread between planets through meteorite fragments. If bacteria on Earth can survive in space, could life on Europa or Titan have come from elsewhere, or been carried there by falling meteorites? These questions not only change our perception of the universe, but also provide important clues about extraterrestrial life. Space experiments help us better understand the ability of life to exist in extreme environments, opening a path for exploring other planets with similar conditions. However, an important lesson about the survival potential of life lies right beneath our feet. In fact, organisms that live in extremely harsh environments on Earth are providing us with valuable clues about the possibility of life existing in extraterrestrial environments that seem impossible to survive. So, could life develop in extreme environments we have never considered? Earth is not lacking in organisms capable of surviving in seemingly uninhabitable environments. They are called extremophiles, organisms that can survive and thrive under conditions so extreme that most other forms of life could not endure. The existence of extremophiles challenges our definition of what conditions are truly necessary for life. Instead of searching only for life on planets with stable temperatures or liquid water, we have begun to expand our search to extremely harsh environments. Heat-loving organisms are a clear example. They can live in boiling hot springs where temperatures can reach nearly 100 degrees Celsius. In such places, water is not the only environment for life. High temperatures and strong acidic chemical reactions are the factors that enable life to develop. Could it be that in hydrothermal vents on planets such as Mars or Europa, life could arise in such extreme environments? The answer may be yes, if organisms are capable of using hydrothermal chemistry as a source of energy. Another fascinating example is salt-loving organisms. They live in hypersaline lakes where the salt concentration is 10 times higher than that of Earth's oceans. This raises an important question. Could life exist in the subsurface oceans of Europa, where the salt concentration is believed to be extremely high? Halophilic bacteria on Earth have developed the ability to adapt to such harsh environments. And they may serve as models for extraterrestrial life under similar conditions. One of the most striking examples is Deinocarchus radiodurans, a bacterium that can withstand extremely high levels of radiation. It can endure radiation doses thousands of times higher than what humans can survive and can repair its DNA after being damaged by radiation. This makes it an ideal model for studying how life could evolve in environments with intense radiation, such as the moons of Jupiter, where radiation levels are extremely high. Could extraterrestrial life develop similar protective mechanisms to survive in the harsh environments of space? While we search for life in environments of extreme heat or intense radiation, another story of extreme life hides deep beneath Earth's oceans. The Hadal Zone, the deepest region of the ocean, is where pressure can be hundreds of times greater than at the surface. Here, tiny organisms such as microbes and crustaceans thrive despite the pressure and harsh conditions. What is remarkable is that organisms living in the Hadal Zone have developed biochemical mechanisms to prevent the breakdown of proteins in cell membranes under extremely high pressure. Could similar organisms be found beneath the icy surfaces of planets such as Europa and Enceladus. Where deep oceans lie beneath thick layers of ice, enduring extreme pressure and freezing temperatures, scientists believe that life in such environments could resemble the organisms living in the Hadal Zone, where living conditions are vastly different from those on Earth's surface. The study of extremophiles and the Hadal Zone not only helps us understand how life can exist in extreme environments on Earth, but also expands our perspective on life beyond the planet. And discoveries about extreme life have completely changed the way we perceive life in the universe. Life does not have to depend on traditional elements such as liquid water and oxygen. Life can develop in any environment that contains liquid and energy. Experiments on microorganisms in space, along with research on the Hadal Zone and extremophiles, have shown us that life is not a rare phenomenon that exists only on Earth. If organisms can survive in extreme conditions on Earth, then extraterrestrial life could also develop in environments we have never imagined. These questions are no longer hypotheses, they are now the goals of modern space exploration. The journey to search for life beyond Earth has taken us across distant, unexplored regions of space. From the frozen oceans on Jupiter's and Saturn's moons, Europa and Enceladus, to places where methane and other organic molecules could serve as solvents for life. At the same time, advanced technologies such as the James Webb Space Telescope have allowed us to look deep into distant exoplanets, opening up unprecedented possibilities in the search for biological traces. Recent discoveries have proven that life is not a rare phenomenon that occurs only on Earth. These data are no longer mere speculation, but concrete evidence, revealing that life could exist in many places throughout the universe. Discovering life beyond Earth is not simply about finding bacteria or simple organisms on other planets. More importantly, it is a process of redefining the nature of who we are. If life exists on another world, even as bacteria beneath ice, or as organisms living in liquid methane, it would prove that life is not a single random event, but an inevitable product of cosmic physics and chemistry. We will continue this journey not only to search for life, but also to gain a deeper understanding of our place within this vast universe. The search for life beyond Earth continues. The discoveries we have made so far are only the first steps, yet it is undeniable that the existence of life beyond Earth is merely a matter of the near future. Opening a new chapter in our quest not only for life, but for a deeper understanding of the universe's true nature and its infinite possibilities. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.